I'll be a little bit sketchy in a few places, and I won't necessarily explain in detail how the Yang-Baxter equation is used, but I'll try to locate specific places where it's used and say it's used here. And hopefully, if you want to learn more, then this kind of thing can be pursued in later talks in the seminar, if you like. So, okay, without further ado, let me start by defining the 6 vertex model. So how this works is that we'll fix some domain lambda in Z2. And at each vertex V and lambda, we'll assign one of 6 possible arrow configurations. And the rule that we enforce or impose in these arrow configurations is that some number of arrows enter any vertex and some number of arrows exit a vertex. And the rule is that the same number of arrows enter as exit. So as you can see in the first, like this A1 vertex, no arrows enter and no arrows exit. In the A2 vertex, 2 arrows enter and 2 arrows exit. And in the remaining 4 of them, 1 arrow enters and 1 arrow exits. So this notion that the same number of arrows must enter and as exit is known as spin configuration, spin conservation, and it simply states the numbers of incoming and outgoing arrows are equal. Okay. So a 6 vertex ensemble is simply an assignment of an arrow configuration to each vertex of lambda in such a way that they're consistent in the obvious sense, namely that if an arrow exits vertically here, then it has to enter vertically right at the vertex above it. So in this way, you can see that the arrows form upright directed paths. The bottommost path might look like this, for example. Hopefully you can see my cursor. Let me know if you can't. Okay, and then you have all these other paths going like that as well. So boundary conditions will play some role in this talk, and they're simply going to be telling you where paths enter and exit lambda. So here we have the so-called domain wall boundary condition, where the paths enter through the left boundary and exit through the top boundary. So, so these are 6 vertex ensembles. So a 6 vertex model is simply a probability measure in all possible 6 vertex ensembles of a domain. So we'll fix some domain lambda again, and we'll fix some 6 vertex ensemble E on it. We'll fix some parameters A1, A2, B1, B2, C1, and C2, which are all positive. And we'll assign each arrow configuration a vertex weight. So here the empty arrow configuration has vertex has weight A1, the full one has weight A2, and I've likewise assigned weights B1, B2, C1, and C2 to the remaining 4 arrow configurations. And the weight of ensemble is simply the products of the weights of its vertices, namely, A1 to the number of A1 vertices times A2 to the number of A2 vertices, etc. So here in this 6 vertex ensemble, you can quickly see that it has the weight in here. I mean, for example, it has 8 empty vertices, which are here, here, and these 6 over here. Okay, so now that we've had weights assigned to the vertices, we can define a probability measure on the set of all possible 6 vertex ensembles on our domain lambda, which is given by the probability of an ensemble E is proportional to the weight of E, and the Z is simply the partition function normalizing constant that makes the sum of the weights equal to 1. Okay, so the physical context, I'll just have a quick slide describing the context in which this model arose. So it was introduced by Pauling in 1935. He was taking all the weights to equal 1, and he took the domain to be a square. It was actually a torus, so periodic boundary conditions. And what he was interested in were these experiments of Jacques and Stout, who were interested in this notion of residual entropy for ice. So he was proposing so Pauling had proposed the 6 vertex model as some model that should compute this residual entropy of ice. I won't go into detail for what exactly that means if you don't know, because I won't really refer to it in the rest of the talk, but it's a curiosity, at least for physical motivation. So he was basically saying that this residual entropy should be given by the free energy, or the 1 over the partition function raised to the power 1 over n squared as n goes to infinity. So he had proposed a heuristic that suggests this free energy should be about 3/2 or 1.5. And the heuristic is as follows. It's a rather naive one, but it's a simple one. So you have about 2 n squared edges in lambda, right? And they can either be occupied or unoccupied. And each of the n squared vertices in lambda, you can have 6 out of 16 possible arrow configurations, right? So you can heuristically imagine, okay, so you have like a 6 out of 16 chance of being, having the correct vertex. By 6 out of 16, I mean there are 6 possible arrow configurations here. But in principle, I could have like 16 possible occupation, unoccupation patterns of the edges, right? I have 4 edges surrounding a given vertex, and they can either be occupied or unoccupied. So in principle, there are 16 possible things that are allowed at each vertex, but only 6 of them are allowed by the ICE rule, the arrow conservation rule. So you have 6 out of 16 of them. You raise that to the n squared, and then you have like 2 n squared edges. So you have you pick 2 to the 2n squared times 6 over 16 to the n squared. You divide that by 1 over n squared, and that happens to be 3/2. The amazing thing, though, which was what excited a lot of people later about the 6 vertex model, was that these experiments actually computed the residual entropy to be very close to that, 1.52. I mean, this is one of the rare situations where the physical model actually gives you almost the correct answer. Not only the physical model, but the a sort of a naive heuristic for the physical model gives you something very close to the exact value. Anyway, so this heuristic is not quite right. Later on, Lieb actually computed the correct value. It's 4/3. It's the square root of 4. It's 4/3 to the 3/2, which is 1.54 about. For the score ice model. And then Lieb, Sutherland, Yang, Sutherland, Yang, and Yang extended this to the arbitrary situation where these weights are general. These A1, A2, B1, B2, C1, C2 weights are not just one, they're general. And they computed the free energy there. So these all are computations for the free energy of the model, the partition, basically the behavior of the partition function. But what we're interested in here is the asymptotic probabilistic behavior. So I'll view this model, as I mentioned before, as a probability distribution on the set of 6 vertex ensembles. And I want to know how the 6 vertex model really looks as this n, the size of the domain, goes to infinity. And here we'll be specializing our attention to the stochastic 6 vertex model, which I will describe next. So the stochastic 6 vertex model is a specialization of the 6 vertex model. I'm going to choose these A1, A2, B1, B2, C1, C2 weights in a specific way that was proposed by Guan Schmon in 1992. So it's the following. We set A1 and A2 equal to 1. B1 and B2 are just going to be arbitrary. B1 and B2, we'll hope they're between 0 and 1. And C1 and C2 will be set to 1 minus B1 and 1 minus B2 respectively. So that B1 plus C1 is equal to 1 and B2 plus C2 is equal to 1. So you might observe that under this, this assignment of weights for any incoming set of arrows. So for example, in this weight here, the B1 weight and the C1 weight, I have 1 vertical arrow incoming. I mean, the way in which arrows exit after that is different, but I mean, I'm fixing that I have exactly 1 vertical arrow incoming and no horizontal arrows incoming. You can see that the sum of the weights of all outgoing possibilities is equal to 1. So here you're seeing that B1 plus 1 minus B1 is 1. Likewise here, these 2 weights, the B2 and the C2 weights, they both have 1 horizontal arrow incoming, and their sum of the weights is equal to 1. These remaining 2, you only have 1 vertex in which no arrows come in, that has weight 1, and you only have 1 vertex where 2 arrows come in, and that also has weight 1. Okay, so this is the notion of the stochastic 6 vertex model, and the reason this case was introduced is that if I fix the places where arrows enter the model, but let them exit wherever they want. I call this free exit data. They're free to exit wherever they like. You can sort of sample this model by a row by row Markovian sampling procedure. So, right here, I've drawn sort of an initial profile for the model. You have arrows exiting at these sites. So I picked the leftmost and bottommost site, which I haven't sort of updated yet, which is over here. It's the bottom left corner of the grid. And I look at my sort of cheat sheet up here, and I see that I have 2 possible ways in which this arrow can go. It can either go up or it can go right. So I flip a coin, and with probability B1, it goes up, and with probability 1 minus B1, it goes right. And then let's say I get tails, so the arrow goes right. Okay, so this happens with probability 1 minus B1. So now I go to the leftmost place, which is the destination of this arrow, which is where my cursor is right now. And I see 2 possible, if I go back to my cheat sheet up here, I see 2 possible places where the arrow can go next. It can either go up or it can keep going right. It goes right with the probability B2 and up with probability 1 minus B2. I flip my coin again, a new coin that's weighted with probability B2 and probability 1 minus B2. And let's say it hits B2, so the arrow keeps on going. And then I flip my coin again, and let's say it lands 1 minus B2, so the arrow goes up, and then I sort of keep on going this way. Okay, so in this way, I've managed to fill in all of the arrows. I mean, all of the, like, I managed to sort of describe what these arrows are doing, how they're exiting this row. Okay, and then I iterate. So I sort of keep going this way, and that's how you can sample the six vertex model, the stochastic six vertex model in this local way. And you can sort of view time as going in the vertical direction here, and you can view this as sort of a Markov process on states in 0, 1 to the z, if you like. Okay, so the basic question we're interested in is, what is the asymptotic behavior of the six vertex model? I've stolen this simulation from Leo Petrov, who has drawn I think it's a 500 by 500 grid. He's taken this stochastic six vertex model, and he's taken the initial the profile in which arrows enter at all possible places on the y-axis and nowhere on the x-axis. This is what we'll often refer to as step boundary data or domain wall boundary data, and he's run it. He's run it. And this is how it looks. Okay, so I'm going to be interested in basically quantifying various aspects of the picture. Those are kind of the questions I'll be focused on in this second third of this talk. And to precisely state this question and the results around it, we'll have to put a number to this model, and that will be done through the so-called height function. Okay, so the height function is defined as follows. So we'll assign an integer to each face of the domain, satisfying these sort of local constraints. Okay, so I've fixed, okay, so this looks kind of complicated, but let me just tell you sort of the pattern here. So so I fixed so there's a vertex in each of these six pictures, and in the bottom left face attached to the vertex, the height function is always h. Okay, and what I'm doing next is I'm sort of telling you how to evolve the height function at the remaining three faces surrounding the vertex, assuming I know the arrow configuration of the vertex. So for example, here, if I have an empty arrow configuration, then the three other faces surrounding the vertex simply copy h. But if I have like sort of this vertical arrow configuration, then the face above h has height function, has the height h, but to the right of h, it has height function h minus 1, and above that it has height function h minus 1 as well. And I've kind of gone around. Okay, so this might seem a little bit contrived at the moment, but I think the real rule is the one that's shown on the right over here. Basically, if I ever have a height function h assigned to a face, whenever I pass an arrow from left to right, the height function drops by 1. And if I don't pass an arrow, the height function stays the same. And likewise here, if I'm going from top to bottom, if I don't cross an arrow, the height function stays the same. And if I do cross an arrow, it goes up by 1. Okay, so the moment I fix the height function anywhere, and I have myself a six vertex ensemble, I can sort of extend the height function to all faces of the ensemble. And this produces a height function h that's defined on the dual. I mean, the dual because it's defined on faces instead of on vertices of lambda. So I can view this h of u as sort of counting how many paths exist to the right of u up to a certain sign. And there's a bijection between six vertex ensembles and height functions up to an overall shift. We'll normally normalize it so that the height function is equal to 0 at the origin. So let me just give you an example. Here I've drawn a quadrant and a six vertex ensemble on it. And I've fixed the height function to be 0 here. And by these rules if you like, you can extend the height function to everywhere else in the quadrant. Okay. And if I only knew the height function, I could recover the six vertex ensemble from it. So there's a back and forth between height functions and six vertex ensembles. The only caveat is that I've fixed the height function to be 0 at the origin, because I mean, of course, if I make it 1 at the origin, I just have to increase everything by 1, and that will give me the same sort of six vertex ensemble. Everything here is up to an overall shift. So yeah, so if I just fix the height function to be 0 at the origin, meaning at this face here, that's just directly in the quadrant that's adjacent to the origin, there's a bijection between six vertex ensembles and height functions. Okay, so now returning to the question of what is the asymptotic behavior of the six vertex model, there are many questions that can be asked, but I'll focus on 3 of them. The first is a limit shape, which is the law of large numbers for this height function h. The second is the fluctuations of this height function. So if I look at h and I subtract away its expectation, for example, how does that behave? And the third are the local statistics, which are limits of local correlation functions. I'll go into that's a little bit vague right now. I'll try to describe in heuristic terms what that means in a little bit more detail later on. Okay, now I should say that this is only the start of a huge domain. There are many more questions you could be asking here. I mean, you can be asking about how the boundary data affects the model. You can be asking, if I make the weights different in different vertices, these are called inhomogeneities, how does that affect the model? I can take sort of weakly asymmetric limits. I mean, those who are aficionados of KPZ know that if you take sort of asymmetric exclusion process, you can scale that, and you'll get a stochastic PDE. You can do the same thing with the six vertex model. You can look at the translation invariant Gibbs states for it. You can add color to it, which I see is one of the topics in the seminar later on. And you can look at non-stochastic variants of the six vertex model. This is, again, there are a huge number of questions you can be asking here. But again, my goal was just to give a flavor of the types of questions we're interested in, and therefore I'll mainly be focused on these three questions for the next few slides. Okay, so what do they look like? What do the questions look like, and what do their answers look like? So, okay, so I will give you an example of a result here. So we'll take the stochastic six vertex model again, and we'll run it under step initial data or step boundary data. And again, I remind you that this is where paths enter at all points to the y-axis. So you see all this black here. I mean, this is meaning that the paths are entering here, and nothing is entering through. This is on the y-axis, and nothing is entering in the x-axis. Okay. So then I can, as I've done before, I can assign a height function to the stochastic six vertex model, and I'll define these. Remember, the stochastic six vertex model depends on these parameters b1 and b2, and using them, I will define these two parameters. Phi is a function, and kappa is a number. So kappa is 1 minus b1 over 1 minus b2, and phi is some function that you get from kappa. Okay, and a theorem. Here's a theorem. So when we fix x and y, so that x and y is between 1 over kappa and kappa. So what I'm doing here, I am fixing it to be between, let me draw. There's this sort of fan here, this cone here. That was a really bad cone, but. So this region x over y is in 1 over kappa to kappa. It means that you're in the interior of this cone. So in that region, you have that n inverse of the height function evaluated at x and yn. So I imagine that I'm looking at some point here, and it's x n yn. And its height function, it's going to scale like n, because I mean you can imagine that if your coordinate is scaling like n, you can imagine that there will be around n paths to the left, to the right of it. So if I divide that out by n, then it will converge to some limiting height function h of xy as n tends to infinity. And here h of xy is given by the sort of explicit quantity, this root, y kappa minus root x squared over kappa minus 1. So I've restricted here when you're in the rarefaction fan. I mean, it's called the rarefaction fan, this cone here. If you're outside of it, then the height function is sort of trivial. It's 0 here. The height function is 0 here, and it's like y minus x here. Okay, so the interesting stuff happens in the interior of this cone, and there it's given by this fancy h. Okay, so this result is referring to the case of step boundary conditions. But if you want a result for general entrance data, however the paths might enter, you have a similar sort of limiting result where this n inverse h of x and yn converges to some limiting profile h of xy. H is no longer going to be given by this explicit quantity here anymore, but instead it's going to be given by the entropy solution to a certain PDE. Okay, so sorry. So, okay, so already, I mean, I know that we're interested in the Yang-Baxter equation here. So maybe I'll give you a curiosity that one could already sort of see from the limit shape here, although I don't really have a Yang-Baxter intuition as to why this should be true. But this kappa here, so this kappa is 1 minus b1 over 1 minus b2. This kappa here does not determine b1 and b2. There are two parameters here, and kappa is only one parameter. So the full behavior, the limiting behavior of the model, what maybe this theorem here, the version of the theorem is telling you, is that for any sort of choice of boundary data, entrance data, the limit shape of the model only depends on this kappa. It doesn't depend on actual on b1 and b2. So you can view b1 and b2 being determined by kappa and this parameter q, which is b1 over b2. So I mean, what these results a direct implication of these results is that the limit shape only determines on the spectral parameter, not on this parameter Q, which is B1 over B2. And that Q is actually the same as the quantization parameter, the UQSL2 that's governing the Yang-Baxter equation for the model. So it's almost counterintuitive in a certain sense, because one often in the Yang-Baxter theory, one often has that you have to fix the Q in the transfer matrices. You can vary the spectral parameter, but here the limit shape is actually dependent of the spectral parameter and independent of the underlying Q. Anyway, that's a sort of a side curiosity. But the basic point here is that here is this sort of limit shape phenomenon. This is one of the questions we're interested in. Okay, next let me talk about fluctuations. So once again, I remind you, Hn is the stochastic six vertex model height function under step initial data. Here are my parameters again. And the statement is that if I look at this h, xn, yn, and I subtract away this limiting guy. So I multiply it by n and I subtract away from it. So I subtract away n times this limiting h, x, y. Then the probability that this is less than some constant, which is explicit, but I won't write it down, times some s times n to the 1/3 is going to converge to this distribution ftws. So let me just make a few points here. The first is that the first question you might ask about the fluctuations is how big are they? Okay, this is telling you that the fluctuations are of order n to the 1/3. Okay, so this is typical for models in the so-called KPZ or Carter-Parisi-Yang universality class. It's different from the n to the 1/2 fluctuations that you often see in Brownian motion or random walks. Okay, so after I've now divided out by this n to the 1/3, so to speak, I can sort of pull it over to the side if you like. The statement is that the probability that this is less than some s is tending to this FTWS. Now, this FTW is the Tracy-Whittem GUE distribution. It governs the law of the largest eigenvalue of a Gaussian unitary matrix in the limit of high dimension. So, I mean, what the theorem is basically telling you is that one, the order of the fluctuations are n to the 1/3, and two, that the limiting fluctuations tend to this Tracy-Whittem law. Okay, so this is the fluctuation. So, sort of physically, I imagine that the six vertex model is supposed to model some sort of atoms or molecules that are interacting, and the limit shape is telling you how we see them on the global scale, like how I would see the thing look. The fluctuations are describing how the molecules are sort of vibrating around the picture that I as a human am sort of seeing. But then the local statistics question is the third one I'm interested in, and that sort of tells you what the atoms are seeing. And what the atoms are seeing is also a physical question, because I mean, you can imagine that the microscopic structure of some sort of molecule or some substance is actually determining the intrinsic properties of the substance, how hard it is or what color it is, and all these things. I mean, you can imagine the difference between graphite and diamond. You can shape them both in a cube, but I mean, it's really what's going on a microscopic scale that determines them. So these local statistics question, which is the third of the three that I'm describing here, is basically trying to understand how this thing looks locally. Okay, so I will consider the stochastic six vertex model with some boundary data. Again, in this picture, I've taken it to be step boundary data, and I'll fix some vertex inside the domain, and I'll consider some order. So this vertex V here is where my cursor is, and I'll consider some order 1 neighborhood around it. So let's say a 10 by 10 neighborhood of V. Okay, so now this isn't scaling with n anymore. It's just some 10 by 10 or 5 by 5 neighborhood of V. Okay, so I now get some, since my original six vertex ensemble is random, I get some random six vertex ensemble when I restricted that neighborhood. Okay, it might look like this. Okay, and the local statistics question is asking you, what is the law of this random ensemble? What is its probability distribution? So this contains all sorts of information about local correlation functions of the model. So what that means is, what local correlation function is, it's the joint law of nearly neighboring arrow configuration. So for example, the probability that a vertical arrow exits from some coordinate x, y, and some coordinate diagonally above it, like x plus 1, y plus 1. The probability that a vertical arrow exits from both of those locations, that would be a local statistic and captured by a local correlation function. Okay, so I'll now can state a theorem about it. So we'll consider the stochastic six vertex model on the quadrant again with some boundary data. We'll let n be some very large integer. Remember, it has some limit shape from these results. Okay, which is given by this fancy mathfrak h. We'll fix some continuity point xy so it's going to be a continuity point of the gradient of h, and we'll let v be some point x, big y. So we should view v as like a point like here. It's scaling with xy, and you can view it as like x times n, y times n, where x little y is given by this sort of macroscopic location. So the location I see when I zoom out. Okay. So the statement is that if I let the gradient of h of xy be minus st, and the reason for the minus s is that you can see from the height function here, this thing is decreasing from left to right. So the gradient in the x direction is going to be negative. So I'm undoing the negative to make s positive. So as n tends to infinity, the statement is that the local statistics around this v will only depend on an explicit way on S and T. So I have not told you what an explicit way means. So to those experts in probability, what I mean by depends in an explicit way is it means that the local statistics converge to the so-called unique translation invariant infinite volume Gibbs measure with slope ST. If you don't know what that means, I mean, don't worry too much about it. But the point is that if once I have a theorem like this, I can explicitly sample from this measure, and I can explicitly compute limiting local probability. So if I let, for example, if I let chi of AB denote the indicator function for an arrow going from AB to AB plus 1, so a vertical arrow exiting from this vertex AB, then a few consequences of this theorem is that the probability that an arrow vertically exits from this xn, yn, so that's chi of x and yn equal to 1. It's the event that the probability that a vertical arrow exits from xy, that's equal to s. So now if I look at the probability that the vertical arrow exits from two adjacent locations, like chi of xy and chi of x plus 1 y, the probability that those are both 1, that's s squared. So that it's just, so in that case, those two events are independent from each other. It's s times s. But now if I imagine these two sites are diagonally adjacent, so I look at the event that a vertical arrow exits from xy and a vertical arrow exits from x plus 1, y plus 1, so just diagonally, up and to the right of it, this probability becomes s squared times this thing, s times 1 minus s times 1 minus b1 times 1 minus b2. So then they're no longer independent anymore. And you can compute all sorts of local statistics of this type using this thing. Okay. So these are the three types of, these are three of many types of results. Fluctuations, limit shape, fluctuations, and local statistics we might be interested in as probabilists in studying this model. Okay. So those are the questions. Now let's go to the tools. How do we do it? Okay. And I should say that not all of these results can be accessed through the method I'm about to describe. And I should also say that there are many more methods than the one I'm about to describe, but this is the one that sort of, I think is quite, maybe it's reasonably close-ish to the types of things that the p-adic world has been doing. One has the Yang-Baxter equation, the Cauchy identities. Those are the types of things that are going to play in the analysis that I'm about to describe. But again, I don't want to burn any bridges. So let me just say that there are many ways of analyzing this model, and this technique is not extensive, but it's rather powerful. It's rather powerful. So I'll take the rest of the talk to go ahead and describe it. Okay. So from now on, I will fix the stochastic six vertex model with step boundary recognition. So that's the only boundary recognition I'll consider for the remainder of this talk, and I'll denote its height function at some vertex xy by h of xy. Again, this is just recalling notation. And I recall that this stochastic six vertex model depends on these weights b1 and b2. And I'll set q equal to b1 over b2. Okay, and that is going to be between 0 and 1. Okay, so the q so we'll define this moment. So ideally, I want to compute statistics of this hxy. That's the game, right? Ideally, one might want to just compute the mean and the variance of hxy. It turns out the thing that's algebraically nicer to compute is a q-deformed moment of this height function. So it's expectation of q to the k times h of xy, where k is if k is 1, it's sort of like a q-deformed mean. If k is 2, it's something like a q-deformed variance. Etc. So the k gives you the level of the moment. So you're raising q to the h and taking a moment of that, if you like. So as I said, these are moments of q to the h, and together, q to the h is a bounded random variable. So if I have all moments of q to the h, I've pinned down the law of q to the h, and therefore just by taking the law, I've managed to pin down the law of h itself. okay? So in particular, one way to analyze this model is to compute these moments, obtain exact formulas for these Q moments. And eventually, again, I remind you, I mean, I'm not necessarily interested in what happens when X is 1 and Y is 2. I want to know what happens when X is like 1 billion and Y is like 2 billion. So I want X and Y to be tending to infinity. So I want the complexity of these formulas to not grow too much with X plus Y. They might grow with K. I mean, I can imagine that even if I take moments of a random walk, I mean, those will get rather complicated as I take higher and higher moments. But I mean, the complexity with the size, I mean, with the size of the domain, X plus Y, or the location of the point I'm testing at, should not grow with X plus Y too much. So, I mean, this is sort of the complication, I mean, the delicacy to this analysis is that one needs formulas for these Q moments that don't get horrendously, I mean, that don't go completely mad if X plus Y goes to infinity. Okay, so here's a sample for how such a formula might look. Okay, so I'm defining psi of xy of w. So this is some function of some variable w. Okay, and it's given by this rational function here. Okay, as you can see, w is playing a role in the arguments of these rational functions, and x plus y are simply x and y are exponents in these functions. Okay, and the statement is that this q moment, this expectation of q to the k times h of x y is equal to, okay, some prefactor times some k-fold contour integral. So there are k integrals here, and k is, again, the level of this moment, times some cross factor. I mean, it's ui minus uj over 1 minus ui over ui minus quuj times the product of these psi's, over ui dui. Okay, so this is an explicit contour integral for this moment. I haven't told you what the contours are, and I won't. This will get too much if I start drawing pictures of these contours. But I mean, this is how it looks. And as you can see here, the complexity of these formulas, indeed, it grows with k, because then I get more contours or more summations, if you like, if I expand these guys. But they don't grow with x and y really, because these are just playing a role in the exponents in the integrand. Okay. So I'm trying to make this claim that to analyze this six vertex model, you want to compute quantities like this. I'm not going to go into this, but let me suppose that you now have this formula. What do you do with it? Okay. Again, so this is sort of, I mean, there's an algebraic component, which is actually getting a formula like this. And then there's an analytic component, which is what to do once you've got it. How do you go from that formula to limit theorems, like this limit shape and the fluctuations and things like that. So, okay, so I'll give you 3 sorts of general methods, but I won't go beyond that. I'll just give you them 2 by name, and then I will proceed to the algebraic part. I mean, this is just to give you some sort of vaguely convince you that these formulas, you can actually do things with them. So the first thing you can try to do is you can take q goes to 1. Okay, so if I do that sort of directly and naively, I have the expectation of 1 to the k times h of xy. That's just 1, not very interesting, right? But what you can instead do is, you can use this formula here, which is that q to the a minus 1 over q minus 1 tends to a as q tends to 1. So if I imagine taking this guy and subtracting off 1 and dividing by q minus 1, and then I let q tend to 1, I've actually gotten a standard moment. I managed to get a moment of h, for example, and I can get moments of h and h squared and h cubed, et cetera, by doing this. Okay, so by doing this, you can analyze the q equals 1 case of the stochastic six vertex model. It's when sorry, I'm going back and forth a lot. It's when this B1 and B2 weights are equal. So the probability of going up is equal to the probability of going right. So like the symmetric version of the stochastic six vertex model. So if I take q to 1, then these q moments become genuine moments, and I can compute them using this integral formula. And if I just want, for example, just the limit shape, then the first 2 moments will give you the limit shape. The first moment will give you the expectation of the limit shape, and the second moment will tell you that it doesn't oscillate around it. So I mean, that will do the job. Okay, so that's one way to just kind of cheat and let q tend to 1. If you're set on letting keeping q equal to 1/2 or something bounded away from 1, then you can sort of collect these q moments into a generating series. So in the case of just standard moments, what one often does is one takes the moment generating series, or just a fancy name for like Laplace transform, which is you look at these h of xy's, you raise them to the k, you multiply by zeta to the k for some parameter zeta, you divide by k factorial. This is simply going to be the exponential e to the zeta of x zeta of h. I take expectations of both sides, and I'm getting sort of the Laplace transform of h defined in terms of its moments. You can do a Q analog of that, and that will give you a Q deformed Laplace transform, which is this guy here, written in terms of its Q moments, which are over here. Okay, and this guy here, you can extract probabilistic information from expectations of this type, just like you can extract them from the Laplace transform. Okay, that's strategy 2. Strategy 3, and there are probably more than these 3, is that, as you can see from this formula, it has a rather generic term, right? I mean, a generic form. It's equal to some k-fold integral times some sort of cross term here, which looks rather generic. I mean, and then times a bunch of independent terms. Okay, and you can imagine that, I mean, this sort of thing occurs again and again in this field. So, I mean, you can imagine that in many cases, I have model 1 and I have model 2, and this formula will be the same for model 1 and model 2. I mean, the size, you can sort of rig them in such a way that the size for these models are exactly equal to each other. And what I mean by, I mean, you can sort of match formulas for this sort of stochastic 6 vertex model with those of a simpler model, and you could try to analyze those simpler models through other means. So, I mean, this bullet point was what I was saying. I mean, these exact expressions, these Q moment type quantities, emit very similar sorts of contour-integral expressions, and in many cases they can be matched exactly, and that can be shown that the probability distributions themselves match. So you can use this to just say that the law of the stochastic 6 vertex model is equal to the law of some other guy, and I can try to compute that other guy with some other technology. Okay, so that said, okay, so these are sorts of what you do once you have moments of this type. So now let me try to spend the remainder of the talk to explain how to get formulas like this. Okay, and I again apologize. This is going to be sort of messy and a little bit heuristic, but I hope it will still explain at least the locations where the Yang-Baxter equation is useful. Although I will not actually show how to use the Yang-Baxter equation there. I will just point to some place and say this is where you're using the Yang-Baxter. Okay, and then I mean maybe in later places in the seminar you can go into those in more detail. Okay, so now let me, so I'm going to encapsulate this 6 vertex model through a random partition, okay? So one runs so I take the stochastic 6 vertex model under step boundary conditions, and I run for some time n, okay? So I'm drawing it here. I have this model, it's on a quadrant, and I run it for time n, which is 4 here. And at level n, I'm going to define this random partition lambda, which is given by lambda 1, lambda 2, all the way to lambda n, which are the locations where vertical arrows exit row n. Okay, so hopefully I didn't make a mistake here. I mean, I hope this is the 7th site, the 5th, the 4th, and the 1st site. So this partition here is 7, 5, 4, 1. Okay, so now the height function h of xn along the nth row, if I sort of probe, if I look at a face here or something like that, and I ask myself how many paths are to the right of it, that's simply determined by the lambda. I mean, you can simply write h of xn is equal to the number of j, so that lambda j is greater than x. Okay, and I'll call this h of lambda of x. It's just another way of writing the height function, but now I just have to think about lambda instead of this whole 6 vertex ensemble. Okay, so to analyze this height function, I mean, I can write it as q to the h of xn, or I can write it as q to the h of lambda x. We'll follow this work of Bourdin and Petrov, and they'll be using Cauchy identities and orthogonality for certain families of symmetric functions to obtain formulas for these Q moments. And I should say that they both of these statements, the Cauchy identities and the orthogonality, they originate from the integrability or the Yang-Baxter equation for the model. The Cauchy identity, I see, is rather maybe familiar to this. To the p-adic end of the audience. I mean, it follows from the Yang-Baxter commutation relations for certain transform matrices. The orthogonality follows from certain summation formulas for symmetric functions. That's facilitated through the algebraic beta-Ansatz, which is also based on the Yang-Baxter commutation relations. Okay, so let me start to explain how this works in a little bit more detail. Again, I apologize. I'm going to be a little bit sketchy here. Okay, so the first thing, okay, so let's let x and y denote these sequences of variables. So the first thing we do, the first thing is one defines a family of symmetric functions, which are denoted by this f of lambda of x and g of lambda of y. Okay, and these are going to be partition functions for certain lattice models, and they're going to depend on an additional parameter s, and that's called the spin. Okay, so I've kind of given you this vague depiction of how these partition functions look like. I have for the F model, I have it under the sort of step type boundary condition where edge arrows enter from the y-axis, don't enter through the x-axis, and they're dropped off at the top boundary according to this lambda. Okay. And G, for this G, they all enter around here for the first site on the bottom. I mean, this first site here where my cursor is, and they again are dropped off according to lambda at the nth row. The weights are okay. I mean, I'm just force feeding you the weights at this point. I mean, maybe it's not important to read them too carefully. For now at least. Okay, they're given by this. I mean, I have weights depending on exactly what the arrow configurations are at each vertex. And using this, I can define partition functions f lambda of x and g lambda of y in this way. So here, x and y are the spectral parameters for the model. They index the rows of the model. And these models, unlike the 6 vertex model, they'll allow multiple arrows to occupy vertical edges. So actually, you see that sort of required for the G, just due to the boundary conditions. I mean, I need to have a lot of arrows entering through here for the G. For the F, if I set s equal to q to the minus 1/2, that will actually, that special point s is equal to q to the minus 1/2 will force a 6 vertex type configuration situation where only one edge can occupy any, one arrow can occupy any edge. Okay. Now I said these are functions, these are partition functions. Their symmetry, I mean, I call them symmetric over here. Their symmetry is actually a consequence of the Yang-Baxter equation. I won't go into that. Again, this is the first of many places where I'll tell you this is a consequence of it and not go that much into detail. But I think Dan already in his previous talk mentioned this point. Okay, so the first step, as I said, is to define these symmetric functions as partition functions. Okay, what next? So the next step, I've simply copied the first step here. The second step is to prove a quotient identity for these symmetric functions. So it takes the form, if I take an f lambda times a g lambda and I sum overall lambda, this has a factorized form. Okay, and I've called this factorized form z of xy. And this is again, okay, the second of many times where I'll tell you that, you know, it follows in the Yang-Baxter equation. I should say that this quotient identity is a fast application of the Yang-Baxter equation, although maybe a little bit not fast enough for me to present it in the remaining time I have here. Okay, but so the second step is to prove a quotient identity for these objects. Okay, so now as of yet, I've sort of just defined these functions and I've defined this, I said they have this nice summation property. The third step is to relate it back to the probability, right? To relate it back to the 6 vertex stochastic 6 vertex model I was interested in. So one can, in just general terms, one can use this quotient identity to describe a probability measure. So the probability of lambda is proportional to this f of lambda of x times g of lambda of y, and then I have to normalize by the z to make the sum equal to 1. Okay, so this is some probability measure. And the point is that the 6 vertex random partition, the one I was describing over here, is a special case of this probability measure. Okay, so it's what you get when you set the x. I mean, so I've, you know, in vague terms, I mean, so when you set the x is equal to something, and I'll call that kappa, and you set the y is equal to something, and you call that kappa, and you set the s equal to q to the minus 1/2. Or remember, the q to the minus 1/2 is what forces the 6 vertex type configuration in the F model. Okay, here kappa will just be the same variable repeated over and over again. It'll be s kappa, etc. And this will basically, by definition, I mean, almost by definition of everything, this will make this f function here, the partition function for this vertex model, almost on the nose equal to the probability of seeing this guy here. I mean, as you can see, the states are identical. It's just a matter of matching weights. And then that match is almost precise up to this factor of minus s to the lambda. Okay, and rho, I'm not going to tell you how to define rho exactly, but it's defined through a certain limiting procedure. And the point is that after I define this rho, the point is that it will make g of lambda of rho equal to this thing, to this factor I was off by. So we'll exactly compensate whatever I was off by. Sorry, this should be a kappa here, not a lambda. And that will make the probability correct. Okay, so I mean, so the point is that this measure lambda, the partition lambda that I was originally interested in, is a special case of this measure by specializing the x and y appropriately, namely according to this kappa and rho. Okay, So I have these symmetric functions. They have a quotient entity. The quotient entity gives rise to a measure, and this measure is related to the probability distribution I was interested in before. And the fourth step is to now insert additional variables into the quotient entity to obtain certain expectation values. So let me now describe how that works.
Hey, Amol,
Yeah.
can I ask you a question about the previous slide? This is Ben. The kappa was the thing that remembered your stochastic weights, right? You had kappa was described in terms of your A's and B's.
The kappa you'll see is the spectral parameter here. It's the 1 minus B1 over 1 minus B2.
So that's how you've like finally remembered the Boltzmann weight of the model that you've set it. And so you could think of the weights that you introduced as a black box for that f of x and g of y as sort of ones that give you the appropriate specialization for those stochastic. Okay.
Yeah.
Good.
Yeah. Any other questions? Okay. If not, I will keep going. Okay. So I remind you. Okay, so I said we have this framework that allows you to write probability distributions of the guy we're interested in terms of these symmetric functions. And now I want to extract probabilistic information about them, right? So I remind you that the probability distribution is like this f of lambda of kappa times g of lambda of rho. And I'll let, okay, so now the way this is going to work is that you're going to introduce an additional variable into the quotient entity. So I let some w be some new auxiliary variable, and I'll let rho of w be rho with another w attached to it. So remember, rho is like some sequence of variables that I'm inserting into the g, and I'm just going to put in an additional variable. I'm going to put in the w now. Okay, so what the quotient entity now tells you is that the sum of f of lambda of kappa. So everything is going to be the same as before, except I'm going to insert this w in the g and see what I get. Okay, so the sum of f of lambda of kappa times g of lambda of this rho and w is equal to this quotient entity here. So I'm just going to write that as simplified sort of. It looks like this. Okay, I might have dropped terms. I mean, this twiddle here, for the purposes of this talk, the twiddle just means pretend it's true. I mean, normally what that means is that you're off by a constant factor or something like this. So I mean, but hopefully just pretend it's true for now. So just taking the quotient entity, you get these 1 minus qxw over 1 minus xw terms, and this will look something like this. So what you get at the end of the day is that if I move this over, so I have 1 minus qs kappa w over 1 minus s kappa w to the n, that's equal to this guy over here. But I can just sort of trivially write that as the sum of f of lambda of kappa times f of g of lambda of rho, and then I take this guy and divide it. I'm just multiplying and dividing by g of lambda of rho. Okay, but then I remember that this thing over here is equal to the probability of lambda, right? So the probability of lambda times this, this quotient, g of lambda of rho of w over g lambda of rho. So that's this step over here. But now this is just by definition equal to an expectation value, right? I'm looking at the probability of lambda times something dependent on value. That's exactly the expectation of that something. So that's equal to the expectation of this guy over here. Okay, and remember that g of lambda, it wasn't an enemy at all. It was rather simple. It was just some factor, right? It was minus s to the lambda. So so the bar of lambda means the total size of lambda, the sum of lambda 1 plus lambda 2 all log to plus lambda whatever L. So at the end of the day, you got that this sort of factor term is equal to the expectation of this some factor, which is minus s to the minus lambda, times this g. Okay, so I've gotten something. Now the question is, what did I get? I mean, I got the expectation of something is equal to something factored. Now the question is, what is this something, and can I use it? Okay, so the fact. Okay, so I've simply written down the previous this previous formula here. So the fact that I will use is that this thing here, the thing inside this expectation, you can compute it explicitly, and it's given by this. Okay, I don't want you to necessarily pay attention to the whole thing. I just want you to note the dependence on W, which is shaded in red here. Okay, I have this rational factor to the lambda I minus 1 times this 1 over SW. Okay, now the point here is that you can sort of extract information from this by contour integration. Okay, more specifically, if I take this red term and I integrate it against this blue factor here, dw of this blue factor here, I pick some integer k and I integrate it. I can sort of I can fish out for the event that lambda I is equal to some k. Okay, and the statement is more or less a triviality. I mean, it's you change variables and it becomes a very standard contour integral identity. So if I integrate both sides of this equation by an appropriate factor, if I multiply both sides of this guy by something by this blue term here, I can start fishing out for terms. Okay, and that's what I've written in this third bullet point here. So I've taken this blue term here, I multiplied it by this expectation, this G thing that I know how to compute. Okay, and what this K term statement here is telling me is that I will get a sum of indicators times these Q to the i's. So maybe I should circle things. See these. Yeah, this Q to the I sticks around. So I'll have these. I'll have those come in, and these will drop down like that. Okay, so that might have been a little bit messy, but okay, hopefully you can believe that if I take this formula and integrate both sides by a specific factor, I will get something like this. Okay, so at the end of the day, what I get is the expectation. So I basically take both sides of this formula up here. I multiply it by this blue term and I integrate. I'll get the expectation of these 1 minus q to the q to the i's times this term here, and it's going to give me some explicit contour integral formula for it. Okay, and that gives you the expectation of q to some power times something dependent on lambda is given by some contour integral expression. Now you can sort of massage this into the q moment formula I've described before. You sort of sum over k, and this will give you a q. This will give you the first q moment formula. It'll give you something like q to the just h of lambda of x, not k times h of the lambda of x, but just h of lambda x, so the first q moment. To obtain higher q moments, you use not one w variable, but many w variables. So I add several w variables into the game, and I will get higher and higher q moments out of this. So just to summarize how this worked is that we defined these symmetric functions, f and g. We showed that they had a quotient identity. We described a measure from them, and we realized the measure that we were interested in as a special case of it. Then we started inserting w variables into this quotient identity, and the quotient identity sort of right off the bat gave you a formula for the expectation value of this g of rho w divided by g of rho. And then we used an exact formula for this g of rho w, and then we sort of integrated it to get some sort of thing that looked like a q moment. Now, the thing that I didn't really explain, I just called it a fact here, was that where does this G formula come from? Okay, so far I've described the quotient identity part. I haven't described the orthogonality part. So the question is, where does this G formula come from? This G formula come from? It's a special case of a more general G formula given by this thing here. So it's a contour integral representation for this G function. Okay, so in the last slide, I mean the next slide is just a summary. And the last slide, I just want to give you a quick, maybe, so how much time do I have? 1 minute, 0 minutes?
1 2 minutes, yes.
Okay. I just want to describe to you where this integral formula comes from, which is where I'm getting, like, you know, the thing that I need to know what I computed the expectation of, right? So this integral formula is what allows me to compute what I found the expectation of. So I will just quickly give you a sketch of where this integral formula comes from. So it comes from the orthogonality relation for f. So what this states is that if I take my f function here and I integrate it against a certain term, okay, this term looks like this. So I pick some partition mu and I multiply it by this sort of cross factor multiplied by this product of rational functions raised to the mu I. So I take 1 minus s of ui over ui minus s. I raise that to the mu I, and if I integrate f against that sort of product, I will get up to maybe a constant. I will get the indicator function for that lambda is equal to mu. Okay. So if I use that fact in the Cauchy identity, so let's skip these 2 bullet points for now. If I use that fact in the Cauchy identity, I can integrate both sides of this Cauchy identity with respect to this factor here that I am highlighting in orange. So I multiply both sides with respect to this thing here. I multiply both sides of that quotient identity by the orange term, and I integrate. That will sort of kill off the f, and that will give me a formula for g of lambda, and it will look something like this, right? I have something like this term. This term is like here-ish, and the orange term is like here-ish. Okay, this is not very well explained, but this orange term is the same as this orange term, and this product here is simply the Cauchy product. So that's the origin of that formula. Now let me undo this mess. Okay, yeah. Okay, so this orthogonality relation, how is it related to the Yang-Baxter equation? It uses a monomial expansion for f, so you can actually write down an explicit formula for f. It's given by some sort of symmetrization identity over here, and the proof of that symmetrization identity is given by is through something called the algebraic beta ansatz, which is also based on the Yang-Baxter integrability. So how this works is sort of you first prove a monomial identity for f using this algebraic beta ansatz. You can start integrating things out, and you'll get some sort of orthogonality relation that looks like this. I put that orthogonality relation into the quotient identity, and then I get the formula for G. Okay, now just to summarize here, sorry if that was a little bit brief. Just to summarize here, I was trying to look at the stochastic six vertex model. It's a specialization of the six vertex model with these stochastic or Markovian weights. I wanted to just describe to you what sorts of questions are of interest to us as probabilists, these limit shapes questions, these fluctuation questions, local statistics. And then I tried to give at least some maybe hopefully vaguely cohesive story about how you can analyze it through the integrability. You prove these explicit contour integral representations for these Q-to-4 moments, and you can prove these formulas through quotient identities in this orthogonality. And both of these quotient identities, the orthogonality, that's where the integrability comes in. That's where the Yang-Baxter equation comes in. Although I did not explain how or where, I just want to pinpoint that this is where you're using it. So maybe later on, yeah, but you can look into that. Okay, so thanks a lot for listening, and I apologize if I went over time.
Thank you so much, Amol. Yeah, this is kind of talk that I was waiting for a long time, so I'm especially happy about this talk. Yeah, let me stop recording.